aspect of gauge theories. So the first point is that all theory of fundamental forces are gauge invariant. Apart from that, they obey the so-called stability theory. Saya sebenarnya tak sempat nak buat latihan lagi untuk buang. Katanya at least untuk semester first half of semester ada 2 latihan yang korang kena buat. Tapi tak apa, nanti saya bagi untuk you buat di dalam cuti semester. Cuti semester. Bagi 2 sekalinya. Okay. So if we represent the let G represent a kind of gauge transformation. Let G, kalau kita gunakan 2 iaitu GXT, maknanya be local gauge transformation operator. Then what happens? What does gauge invariance require? Where the Lagrangian contains some wave function, tak kisahlah whether this wave function represent the interaction in any of these fundamental forces. So this will give a Lagrangian sum, but now the wave function is slightly different. Okay. So in general, actually V1, tapi in general dia tak sama. In general, once this G acts on a Lagrangian, is not equal to this. Sorry, there is another one here which should be star. Sorry, in general, tak payah tulis in general sebab saya dah sambung di sini. So di star ni menunjukkan bahawa G gauge transformation ni mengubah, kalau dia hanya Lagrangian, Lagrangian is the same, only the wave function berubah, dia tak memeriksa, so it's equal. But if the L itself transform into another one, L star, then in general this is not equal. So unless we introduce a new field inside the Lagrangian, saya tak payah tulis inside the Lagrangian lah. Katakan G ni bertindak pada L, dan dalam L ni sebetulnya ada psi dan ada A. So this become L psi star A star, which is actually also equal to L star psi star A star. So in general, we always need a new field that allow L to be equal to some L star. Okay. So itu cara how you make the Lagrangian to invariant. So this is a general apa? It's a general method. It's a general mathematical method that you add something extra to make the Lagrangian have the same structure. Yeah? The transform Lagrangian have the same structure with the original Lagrangian. The original Lagrangian yang ini, yang L star ni yang dah di operasikan. Okay. Dalam kes quantum electrodynamic, this A field is the photon field. For example, in EM interaction or quantum electrodynamic, A represent photon field. So actually, this A is a vector field. And then if we focus on EM in general, to be more specific, we require this G, L, psi 1, psi 2, A, okay, to transform as L, psi 1 star, psi 2 star, A. Why this psi 1 and psi 2? You know, when you have an interaction at 2 points, say there is an electron here and electron here. So this electron number 1 is electron number 2. For any interaction, you need at least 2 particles. You are not going to study interaction of particle with itself. It's meaningless. So this A actually describes this photon that connect the two electrons. See, electron, electron. So in general, it is always better to write in psi 1, psi 2 like this to describe that A describe this interaction field. So the force in general will change the phase of wave function. So force or a force in general will change the phase of wave function. But that's okay, because last time we discussed that if psi is transformed into a psi E minus I omega T or something, not omega, some lambda, where this lambda depend on x t. So this is the phase. So that doesn't matter. Sorry, this will be under. I cannot write a G here. This phase transformation. Why? Because the G act only on the Lagrangian. But within the Lagrangian there is the psi, the wave function. Okay. So this is under gate transformation. This is what happened. And any phase change here does not change the physics, because we saw last time that it does not change the probability. It does not change the current. Now let's look at the third point, what we call hierarchy of the gauge force. call hierarchy of each force. Now so here I will give you a kind of toy model, not the real model but toy. We play around with this model first. So under gauge transformation, psi become psi time E I say, it could be minus or plus, doesn't matter actually. Yeah, so E I say alpha x. Forget about t first. And then say in the case of EM, for EM, remember for EM, I mean we take the simplest also. For EM, the del become a del minus IA x. That was the transformation. And this mean that, or you can also make equal transformation, that A transform into a x. I mean these are all vectors plus del of alpha x. So that we already say something about that in the last lecture. Now in so this del is in a vector form, but if you generalize to tensor, what does this mean? This the gradient is written in d by dx, where x is of many dimension with the index mu. So this one will transform into a gradient that looks like the original gradient I E A mu. Also the apa ni, in 3 dimension become in 4 dimension. Apa ni, tensor, in tensor form. And this one, so this one also the A also transform into a tensor form. So I don't have to derive this, but just believe me that this is the normal way of from the tensor, from the vector to the tensor form. Now, I have not teach you a Klein-Gordon equation or Dirac equation, but you can do some reading there, that you can this Klein-Gordon equation is another equation that try to generalize Schrödinger. Okay? And apparently this is true for scalar particles. So any scalar particle. So this is this will follow the, so it can be, so this, the covariant and the contravariant component of the differential, okay, plus a mass square acting on the wave function pi is 0. So this is called the Klein-Gordon equation. And this wave function is for a scalar particle. Whereas a generalization of the Klein-Gordon, which is the direct equation, is for vector particle. Or so here he generalized it to I gamma mu G mu minus M. Mu ni bukan apa, dia index, subscript and superscript. So scalar mean describing energy momentum. Okay. Yang ini, not only that, it describe energy momentum but also speed. It describe, so this is a vector particle. So the wave function describes a vector particle, and this mu is called the direct matrix. So that is just to show you that, and then you can go on and on to describe this. And actually, all this equation, or rather the equation of motion ini, can be derived from a certain Lagrangian. So very complicated. So I don't want to go into that. Now let's look one by one. I mean, because this is just macam structure of this theory without going into the detail. Let's look at, say, weak interaction in this picture. So in this picture, what happened was you have weak interaction typically involve lepton and neutrino. Okay. So this is the neutrino of the particular lepton, and usually you have a transformation into another lepton. Okay. So the phase transformation will be some. So the phase transformation. So the gauge transformation, sorry, will involve some psi, ei, some g, a dot tau, and this tau actually is called so the tau is called the weak isospace. So tau represent matrices in weak isospace, and in general you have tau plus 0 square root to 0, 0, tau minus 0, 0 to tau 0 would be 1 minus 1, 0, 0. So these three are called the generators of SU2. So if you look here, the number is a 2 by 2 matrix. The transformation involve a 2 by 2 matrix. So there are 2 by 2 equal to 4, but only 3 are independent. So that will be, because usually if you have 4 elements like this, the final element is usually determined by the other 4, by the other 3. But the last element is not independent. It's dependent on the other 3. So there are 4 minus 1 equal 3. A gauge goes on. So this is the W plus, W minus, Z0.